It's tempting to think that quantum mechanics is just a theory about tiny particles, nothing more. But what if I told you that it might suggest that you can never truly die? Quantum immortality. Quantum theory shows us that the world behaves in ways that defy classical certainty, famously described by Einstein as God rolling dice. Left alone, particles don't have definite positions or velocities. They are everywhere and nowhere simultaneously. In truth, quantum mechanics is perhaps best understood as a theory of overlapping states. For example, an isolated electron does not have a fixed spin-up or spin-down state. Rather, it is literally in a blend of both at once. It's only when we observe it that the electron appears to decide. This behavior is most clearly illustrated with the famous double-slit experiment. Gradually shoot just one electron at a time toward a wall with two small openings in it, and you'll get an interference pattern on the other side. Somehow, even a single electron behaves as if it moves through both slits simultaneously, producing that interference pattern. Indeed, the electron acts just like a wave, with phase peaks constructively combining to create ridges and minima combining into dips. But if we place a detector on one of those openings, thereby allowing us to track which path it took, the interference pattern disappears and we're left with two marks. They now seem to behave like particles. The consequences of this simple experiment are perhaps the most profound in all of physics. It deeply unsettles our ordinary intuition and reveals quite clearly that the universe is not what it appears. If you feel puzzled or astonished by this, then you're in good company. Even Richard Feynman, who helped develop quantum electrodynamics, famously stated, "I think I can safely say that nobody understands quantum mechanics." And so physicists and philosophers have debated for a century about what quantum mechanics truly implies for the nature of reality. One thing they do largely agree on is that prior to any measurement, the nature and evolution of these superposition states can be described like a wave. Indeed, we call this the wave function, first written down by Erwin Schrödinger 100 years ago. The real question is, how does this quantum wave-like state suddenly transform into the more familiar classical particle-like behavior after measurement? For decades, the dominant view has been the Copenhagen interpretation. That is, these superposition states remain until they are observed, at which point they collapse into a single definite state with a probability given by the Born rule. That is a probability given by the square of the wave function. This certainly produces exquisite agreement with experiment. Indeed, it is arguably the most precisely tested theory in all of science, verified to within parts per trillion accuracy, but it doesn't explain ontologically what's truly happening. First off, it's important to say that most physicists reject the notion that wave function collapse in any way involves human consciousness. Instead, these measurements could simply be an interaction with the environment, such as a stray photon near one of the slits. But then here's the issue. Surely that photon then also becomes mixed up in the superposition, a combination of striking the electron and not striking it. Certainly we know that superpositions are not limited to single particles. Entire ensembles can be in a superposition too, in which case we describe them as being entangled with another. In fact, that is the foundation behind quantum computing, teleportation, and cryptography. So as our electrons from earlier proliferate out into the broader world, then surely too shouldn't this superposition state, this march of entanglement spread out too, eventually even encompassing human observers. But of course the problem is that in our everyday life, we do not experience any form of superposition effects, so surely something is missing here. This strangeness is most vividly highlighted with the infamous Schrödinger cat experiment. Imagine a cat in a box with a bottle of poison that will break open at a certain time with a 50-50 probability governed by the outcome of a quantum measurement, say whether an electron is spin up or spin down. Now, after the critical moment passes, the electron can be described as being in a superposition of both states. And since the measurement device is entangled with this quantum system, then so too must be the cat, existing in a bizarre superposition of being both dead and alive. Wave function collapse via the Copenhagen interpretation at first seems to resolve this paradox, but it comes with many puzzles. For example, why is it that the observer, be it a stray photon or the cat, or indeed we who open the box, are allowed to be treated as somehow distinct classical entities, whereas the electron has to be considered quantum? Surely everything deep down is fundamentally quantum. There's also no mechanism for this mysterious unitary and frankly ad hoc wave function collapse. And so unsurprisingly, debate has persisted for decades about what quantum theory truly means. I sincerely hope that this will be the final time that I find myself here. You simply don't understand, do you, Jean-Luc? The trial never ends. In 1957, Princeton graduate student Hugh Everett proposed a bold alternative interpretation. Simply, the wave function never collapses, ever. Collapse implies that the other states in the superposition simply vanish, and only one continues. Everett suggested that all possible outcomes of a quantum measurement occur, evolving in separate, non-interacting branches of reality. This so-called many worlds interpretation was, for a long time, largely disregarded by the physics community, but in the last decade or so, it has emerged as a serious contender, championed by the likes of Sean Carroll, David Deutsch, and Max Tegmark. You know, Everett's idea is actually quite straightforward. He just takes the Schrödinger equation completely literally. There is no collapse in that equation, and so that means that the electron, the box, the cat, you, me, indeed the entire cosmos are described by one gigantic wave function, often called the universal wave function. In place of collapse, the many worlds interpretation explains the classical appearance of our macroscopic world by a concept known as decoherence. So the question is this: if the entire universe is in a superposition, then why don't branches interfere with each other like they do in the double-slit experiment? The answer lies in phase coherence. In simple systems, quantum waves remain in sync, and that allows them to interfere. But in complex systems, interactions with countless particles scramble their phases. The result, a clean split between worlds known as decoherence. Subtly, this branching of realities is not an abrupt event. It unfolds as the decoherence spreads, exponentially suppressing interference between different quantum branches. After decoherence, the universes can no longer exert any cause or influence on one another. So no, sadly, you can't create a Council of Ricks. Yet the number of universes here would be staggering because this branching has been happening since the Big Bang itself and across the entire cosmos. You can even generate new universes yourself using the Universe Splitter app. This is not sponsored, where you can base your decisions off a quantum measurement made over in Switzerland. So in this branch of reality, I'm posting this video at 2:00 p.m, but in another, I posted it at 1:00 p.m. Both truly happened. But if this whole idea of splitting unsettles you, well, you're not alone. Theoretical physicist Bryce DeWitt is said to have visited Everett and praised him for the elegance of the mathematics behind his idea, but admitted that he was disturbed by the gut feeling that he didn't feel like he was constantly dividing into parallel versions of himself. Everett is said to have coolly replied, "Do you feel like you're orbiting the sun at 30 kilometers per second? Touché," DeWitt said, conceding the point on the spot. "You think that's air you're breathing now?" Among physicists, the many worlds interpretation has increased in popularity thanks to its rigorous adherence to the Schrödinger equation. But as the concept has gained momentum, many have realized that it implies a strange and radical consequence. The idea can best be pictured as a game of quantum Russian roulette, popularized by Max Tegmark in his book Our Mathematical Universe. He describes a quantum machine gun which can fire once per second depending on the outcome of a quantum measurement. Specifically, each time the gun is triggered, it places a particle into a superposition where it's equally likely to be in two states at once, for instance, spin up and spin down, and then it measures that particle. If it's spin down, the gun fires and kills you faster than human perception. Else, it just makes an audible click, and it repeats this every second. Now, according to Everett, there will be two parallel universes after the first second, one where you are dead and another where you are alive. In other words, there is exactly one version of you with perceptions and a stream of consciousness both before and after the experiment. Since you can't experience not being alive, the prediction is that you will hear an audible click and survive this measurement with 100% certainty. And of course, what's truly bizarre is that you could sit there and hear dozens of clicks in a row, somehow surviving time after time. After 40 consecutive clicks, the Copenhagen interpretation says there's a 1 in a trillion chance you'd still be alive. But Many Worlds says there will be, with 100% confidence, a version of you that survives this extraordinary sequence of events, allowing you to conclude that Everett's idea was right all along. In effect, then, you could demonstrate that the Many Worlds interpretation is correct, but it would be an oddly private proof. In the vast majority of the parallel universes, everyone else would simply watch you die, baffled as to why you attempted such a thing. They would never witness your proof, and so the experiment fails to convince anyone else. Although Hugh Everett never wrote directly about this idea, Eugene Shkovtsev's biography states, Everett firmly believed that his many worlds theory guaranteed him immortality. He argued that his consciousness, at each branching, is compelled to follow whichever path does not lead to death, and so on, without end. Sadly, at least in our branch, Everett's own life was difficult. After widespread rejection, he became increasingly withdrawn, failed to obtain an academic post, drank and smoked excessively, and eventually died of a heart attack at age 51. Now, Tegmark is very clear that this is not an experiment he recommends you try yourself. I want to emphasize that point as well. It would be unbelievably reckless and foolish to engage in such an experiment at home, and it will become obvious why as the video continues. Hypothetically though, Tegmark says there are 3 conditions that would make this macabre experiment actually work. The random decisions must be genuinely quantum. It must kill you or render you unconscious faster than you can perceive. It must truly kill you, not merely injure you severely. Meet those 3 conditions and, the argument goes, you would somehow survive time after 2. Yes, I am invincible. In a 2001 lecture, philosopher David Lewis expanded this quantum Russian roulette into a form of broad immortality. He reasoned that since the entire universe is ultimately governed by quantum events, all causes of death meet Tegmark's first and third criteria. For instance, if a car is about to strike you, there is an infinitesimal probability it will quantum tunnel straight through you without harm, and according to Many Worlds, some version of you must survive such events. If Lewis is right, each of us will one day gain personal evidence for Many Worlds, seeming to escape fatal car crashes, survive severe illnesses, and eventually outlive friends and family. Tegmark, however, diverges from Lewis's view because of his second criterion. Most causes of death are not faster than our perception. They are typically a slow decay of our mental or bodily faculties, something we can experience over time. But even this, Lewis anticipated, with a grim and disturbing prediction. He conceded that you will indeed deteriorate, but all you need to do is survive each moment, not emerge healthy. Over time, you would accumulate ever more damage, like the Struldbrugs from Gulliver's Travels, or the protagonist of Death Becomes Her. Lewis wrote, as you survive deadly danger over and over again, you should also expect repeated harms. You should expect to lose loved ones, your eyes and limbs, your mental powers and your health. Eternal life on such terms amounts to a life of eternal torment. Is that the fate that awaits us all? Eowyn, my body is broken. You have to let me go. Since quantum immortality is so deeply personal, an important question to ask is whether our own experiences of the world truly align with its predictions. So let's revisit the first half of Tegmark's second criterion, that you must either die or lose consciousness. It's already non-trivial for Tegmark to treat those 2 states as equivalent, but I suppose the reasoning is that in neither case can you perceive anything. Physicist Anthony Aguirre explores this idea in his book Cosmological Koans, reflecting on what it means when we are anesthetized or even asleep, experiences we can all relate to. One could argue that we should always continue along the branch where we stayed awake indefinitely, since the branches where we fall asleep are imperceptible to us. But of course, even while sleeping, there is a reduced form of awareness, such as dreaming. More importantly, those diminished states of consciousness are not permanent. Skip forward 8 hours in both branches, and you will again encounter a conscious version of yourself. Another Anthropic-style challenge invokes the mediocrity principle. If we truly live forever in increasingly decrepit states, then there would be far more years of existence in that frail condition than in the relative youth we now enjoy. In fact, within the story of your existence, it would be astonishingly unlikely that you happen to occupy this present, normal-aged moment rather than one of those endless Struldbrug years. I think this offers a compelling counter-argument, but it's the same reasoning used in the Doomsday argument or Boltzmann brain discussions, all of which can be questioned on the issue of reference class. Perhaps your future condition is fundamentally different from your current one, in which case you may still occupy a fairly ordinary position within your present reference class, namely being youthful. Despite our best attempts, these concerns cannot deliver a definitive blow against quantum immortality, but if we revisit Lewis's reasoning, we uncover a questionable assumption that undermines the entire proposal, an assumption about how the universe itself operates. If there's nothing wrong with me, maybe there's something wrong with the universe. A central pillar in David Lewis's case for immortality is what he calls the corrected intensity rule, a concept that highlights one of the most persistent tensions in debates about the many worlds interpretation. Suppose a life-threatening quantum-triggered event produces 4 distinct, equally likely outcomes in which you perish in 3 of them. Under the Copenhagen interpretation, we would assign a 25% probability to each using the Born rule, with only one outcome realized. But in many worlds, all 4 occur with 100% certainty. Of course, if everything happens with equal certainty, then the theory risks losing predictive value. Everettians address this by arguing that each branch occurs with a certain measure of existence, a kind of intensity, here 25% each, again derived from the Born rule. Now, since your consciousness can only occupy one branch at a time, you might conclude there's a 75% chance of dying in this grim scenario, even under many worlds. But Lewis's move here is to discard all branches where you die, because as he puts it, death is oblivion. The experience of being dead cannot be expected to any degree, because there is no such experience at all. By renormalizing only the surviving branches, Lewis arrives at his corrected intensity rule. This step is pivotal to the case for quantum immortality, but many philosophers take issue with this sleight of hand. For example, David Papineau writes, "It is by no means obvious why Everettians should modify their intensity rule in this way, for it seems entirely reasonable to apply the unmodified intensity rule in life or death situations, just as in all other contexts." Many worlds advocate David Deutsch also pushes back, writing in his book, "This way of applying probabilities does not follow directly from quantum theory as the standard approach does. It requires an additional assumption, namely, that when making decisions, one should disregard the histories in which the decision maker is absent. My suspicion is that this assumption is false. In other words, when the universe branches, there is no guarantee that you personally continue along the path in which you survive. I didn't think it would end this way. End? Oh, the journey doesn't end here. Death is just another path, one that we all must take." I think Papineau and Deutsch make compelling arguments. It's certainly unclear that we can simply ignore death branches in the way Lewis prescribes, yet neither of them can definitively falsify Lewis's claim either. Yes, Lewis introduces an additional assumption, but that doesn't automatically make it false, and it stems from a line of reasoning that is at least internally consistent. The problem is that quantum strangeness makes it extremely difficult to distinguish between what is genuinely real and what is merely a theoretical artifact, so perhaps it helps to think in terms of more conventional analogies. Leaving aside the broader idea of generalized immortality for now, let's return to the sharper case of Tegmark's quantum Russian roulette. A thought-provoking analogy here is to imagine a Star Trek transporter. It beams you up and rematerializes you elsewhere. Before transport, there is one of you. Afterward, there is still one of you. In the series, characters rarely seem troubled by this process, so let's assume it's perfectly safe and not secretly a death machine. But suppose a malfunction creates two versions of you instead. Strictly in terms of your survival, this shouldn't disturb you. You continue regardless, even though of cloning you raises ethical concerns. This splitting is essentially analogous to what happens under the many worlds framework. Your consciousness, the you, can only inhabit one body at a time, and yet both versions would insist they were the genuine continuation. So which one is truly you? Now, add a darker twist. Suppose one of the two rematerializations fails, leaving only a gruesome mess on the transporter pad. Understandably, you might hesitate to step into that transporter since it appears there's a 50% chance of death, but consider that failed version never formed enough coherence to host consciousness. It never had an I to experience anything. So is it really possible for you to become that puddle of flesh? And we can push this one step further. Imagine the crew detects the malfunction before rematerialization even occurs and deletes the corrupted pattern file inside the computer. In this case, aren't we essentially back to the original one-to-one transporter scenario? The very case in which few people raised objections. To be fair, I promised a conventional analogy and then started talking about sci-fi transporters. The fact that no one actually knows how such a device would work perhaps only adds more confusion to the discussion. So let's consider instead a classical analogy that Sean Carroll uses in Something Deeply Hidden. Lewis's entire argument rests on the claim that you shouldn't be bothered about the branches where you die because you can't experience them. But Carroll strongly rejects this. After all, if someone crept up behind you with a gun and instantly killed you, you would not be okay with that. The fact that you can't experience being dead is irrelevant. It's perfectly rational not to want to be killed, regardless of whether death is consciously felt. The reason we don't want to die isn't only that we experience pain, Carroll notes. Prospectively right now, the idea of being dead in the future disturbs me. If someone told me I'd die on a specific date, that might be useful information, but if that date was soon, I'd be sad. And the same principle applies to the Quantum Immortality experiment. I don't accept the move that says, well, in all the branches where you're dead, it doesn't matter because you're dead and can't feel anything. Unfortunately, David Lewis died shortly after giving the lecture that sparked much of the quantum immortality debate. But one imagines he would have pushed back on Carroll's scenario as being categorically different. In Carroll's example, you truly and finally die. Lewis would insist that in the quantum picture, your stream of consciousness continues uninterrupted. It's understandable to be disturbed by the finality of Carroll's classical thought experiment, but Lewis's central point is that in the quantum version, there is no such finality. Max Tegmark may have popularized the quantum Russian roulette experiment, but it's interesting that he later softened his stance on whether one would actually survive it. As we noted earlier, Tegmark emphasizes that most real-world deaths fail his second criterion, happening on a timescale shorter than human perception, but it's far from obvious that this safeguard really guarantees continuity of consciousness. In particular, philosopher Charles Sevens argues that the timescale is irrelevant. Once the quantum gun fires, the universe has already branched even before the bullet strikes you. Both versions are legitimately you, and in one of them, you die. That single point alone is a powerful reason never to attempt this experiment, because in reality no physical process is truly instantaneous. Tegmark and others are also unsettled by another thorny issue: how many worlds actually treats probabilities, or measures of existence, across different branches. This, perhaps more than anything else, is what critics seize on. How can all of these outcomes occur with 100% probability? For example, after a large number of Russian roulette trials, the proportion of worlds in which you survive becomes astronomically small. Shouldn't this disturb you? Physicist Lev Vaidman thinks so, writing that the overwhelmingly larger measure of worlds where you're dead is a good reason never to play this game. But then again, aren't we all already low measure? Since the Big Bang, unfathomable numbers of branchings have occurred. The set of worlds in which you happen to exist right now, alive, born, and conscious, is vanishingly small. By that logic, you shouldn't even really be here. We've all been dancing around the basic issue. Does data have a soul? I don't know that he does. I don't know that I do. But I have to give him the freedom to explore that question himself. And so we arrive at the heart of it. This bizarre notion is as much about the philosophy of mind as it is about quantum mechanics. Lurking behind the entire discussion is the question, what does it really mean to say you, your consciousness, your identity, your selfhood? This is arguably humanity's oldest and most difficult riddle, and unsurprisingly, no consensus exists. My Columbia colleague Brian Greene frames it like this: each copy is you. The challenge is simply to expand your idea of you beyond its parochial boundaries. Each branch has its own consciousness, and each version sincerely believes they are you. The real you, Greene suggests, is their collective sum. Lev Vaidman takes a more grounded stance. There are many different Levs in different worlds, but it is meaningless to say there is another I. There are beings identical to me at the moment of splitting in each branch, and all of them came from the same source, me right now. Philosopher David Wallace presses this tension further. For him, the concept of I can only make sense if identity is confined to a single branch of the multiverse. Since it's unclear how such confinement could work, Wallace concludes that many worlds may not actually describe multiple selves at all. Instead, it may dismantle the very idea of selfhood itself. It denies any deep meaning to you, and I can't help but be reminded of another raging debate in quantum theory, the black hole information paradox. Here, quantum mechanics collides with selfhood, and once again, the result seems to be that something fundamental eludes our understanding. Cosmologist Anthony Aguirre argues that the entire quantum immortality debate can be seen as a reductio ad absurdum, a proof by contradiction of our current grasp of both many worlds and the theory of mind. For that one fraction of a second, you are open to options you had never considered. That is the exploration that awaits you, not mapping stars and studying nebulae, but charting the unknown possibilities of existence. On October 27, 1962, at the height of the Cuban Missile Crisis, a Soviet submarine near Cuba was surrounded by American destroyers and forced to dive deep to avoid detection. Cut off from Moscow, the Americans began dropping practice depth charges, meant only as a signal, but the Soviet captain believed they were real and ordered the launch of a 10-kiloton nuclear torpedo. His political officer agreed. Only the second officer, Vasily Arkhipov, refused and persuaded his captain to stand down. World War III did not happen that day, and of course, if it had, most of us would not be here. In the many worlds interpretation, we could never occupy a branch where that nuclear exchange occurred because we would all be dead. Perhaps all of history is just such a sequence of wildly improbable escapes, events, that somehow conspired to bring you here. In the branches where they didn't, you simply aren't there. What happened? Instead of firing, they suddenly disarmed and cancelled. Fate protects fools, little children, and ships named Enterprise. It's easy, maybe even lazy, to dismiss quantum immortality because it feels absurd. It's much harder to rigorously refute it without abandoning many worlds entirely. These kinds of Gedanken experiments, thought experiments, mark the edge of our understanding, showing us where the road ends. And like the black hole information paradox, there's something profound here, a lesson about who we really are and the nature of reality. Even if many worlds is true, Lewis's vision of Stolberg-style immortality is a bitter pill. After all, many worlds does not mean anything can happen. Outcomes still emerge from the laws of physics. More tellingly, it seems far more likely that we would each be inhabiting a much older state than the relatively youthful one we enjoy now. Yet we are not. Still, there's a strange silver lining. Even if we throw out the question of who is really you across the branches, in those other branches, doppelgangers of you and me are living their lives. Even critics of quantum immortality, such as Peter Lewis in his book Quantum Ontology, concede this much. Certainly, the many worlds theory has the following consequence. At any future time, there is a branch containing a living successor of you. So perhaps, somewhere out there, Hugh Everett is still alive at 94, surrounded by great-grandchildren and a long overdue Nobel Prize. David Lewis has popped over for a friendly game of chess to continue their debate on quantum immortality. Amongst those countless other branches, we can indulge the thought that all our hopes and dreams, a better world, a happier life, are playing out. And even though we can never step into those island universes where we made different choices, where our loved ones lived longer, or where history took another turn, their existence proves something extraordinary. Those dreams are realizable. And perhaps, even if we can never reach those other worlds, the thought that they exist can be a quiet source of comfort and inspiration. After all, reality may be stranger and richer than we can possibly imagine. So until next time, stay thoughtful and stay curious.